Hello students, let's begin lesson 7. The normal probability distribution. Previously in lesson 6, we studied discrete random variables. And now let's consider continuous random variables. There are many, but out of all those examples of continuous random variables, by far the most important one is the class of normal random variables. And that's what we're going to focus upon here, the normal probability distribution. Alright, let's begin. I just mentioned continuous random variable. What do you mean by that? Well, here's a definition. A random variable is said to be continuous if its cumulative distribution function is continuous. Great. Remember the CDF? It's a function defined like this. That's a continuous function, increasing from 0 to 1, so it's differentiable almost everywhere, and the derivative is going to be called the probability density function and so on. Oh, we have a problem. We can't do this because we don't have calculus here. It's getting too deep, too difficult, too quickly. So, instead, let's take a long way around. Instead of using calculus, let's go back to lesson 6 and let's begin with a review. It's a long way around, but it's a method that you can actually understand. Alright, here are a couple of review questions. Number 1, what is a random variable? Number 2, what do you mean by a probability distribution? I hope everybody remembers, but just in case, a random variable is a scheme that assigns a numerical value to each outcome of the sample space. More formally speaking, it's a real valued function defined on the sample space. Here's an example, the same example we went through before in lesson 6, so let me be brief. In an urn, we have some colored balls, so the sample space is RGB, red, green, and blue. None of them is a number, so the kind of mathematics we can do is rather limited. Yes, here are some numbers, so we can do some counting and do some probability computation, but that's about it. However, what if we assign some numbers like this? Instead of RGB, let's assign 0, 2, and 3 respectively. Or maybe like this. And of course, there are still different ways, and many more. In any case, if we assign a numerical value to each outcome of the sample space, we can do a whole lot more mathematics, such as the expected value or the mean, the variance, and the standard deviation. And I hope everybody remembers what they mean, what they stand for. So much for random variables and some important concepts from lesson 6. But please remember, all those are about discrete random variables. As you can see, we are dealing with only a discrete set of values. Now, for discrete random variables, you have to remember two humongously important functions. Number 1, the probability mass function defined like this, and number 2, the cumulative distribution function defined like that. These are real deals, and put those two together as a single entity, and we're going to call it the probability distribution. Let me reiterate that. The probability distribution of a discrete random variable is its PMF and CDF put together. Now let's go back to PMF and CDF and dig those a little bit deeper. CDF first. It's defined as the probability, or more precisely speaking, the cumulative probability that the random variable capital X is taking a numerical value small x or less. We don't need precise equality, equal to x or less. Here's an example, and here is the graph. And that's perfectly okay because we don't need precise equality. You can use this everywhere for all kinds of random variables. Now let's go to PMF, and that's going to be a little bit problematic because we have equality here. The probability mass function is defined as the probability that the random variable is taking the numerical value small x precisely. We need a precise hit. And that's not a problem if we have just a finite set of x values like this. and the non-trivial probabilities, and otherwise all 0. In that case, we have graph like that. Even if we have not just 4 but 40,000, no problem. Even if we have infinitely many, as long as they're all discrete, such as set of all positive real numbers, we can make it work, like Poisson random variable. But we are going to deal with continuous random variable now, so we have to have a continuum. We need an interval, such as interval 0 to 1, or 0 to infinity, or negative infinity to positive infinity, those kind of things. In that case, we have uncountably many x values, and out of that uncountably many, the concentration, or the contribution of just one x value, that's nothing. I mean, we can have some concentration, but just one point out of uncountably many, that's not going to give you anything. If you force your definition like that, you're going to get either 0 or undefined. In short, the probability mass function, that concept breaks down. Now the cumulative distribution function, that's okay. So for probability distribution, we needed these two, but PMF is not working. So we're going to need a replacement here. How do we do that? Now, let's go back to 1.2 and let's bring this back. CDF is okay. We don't have PMF, so we need a replacement. Let's introduce a new function called the probability density function with the following properties. The probability density is always non-negative, greater than or equal to 0 all the time. And number 2, toward positive infinity and negative infinity, it goes down to 0. And finally, number 3, the real deal. As you can see from these two pictures, the probability corresponds to the area. Area underneath the curve above the x-axis and between A and B, as you can see from this blue region and the red region. And that's the essence of probability density function. Now, how are these two related? CDF and PDF? That's a difficult question, and that'll require calculus. It's actually the derivative-antiderivative relationship, but let's not go too deeply into that. Instead, let's focus upon these three properties here. Number 1, that's easy, as you can see from these two pictures above the x-axis. That too is easy, as you can see here, toward the left-hand side and right-hand side, going down to 0. Yes, we have asymptotic behavior, horizontal asymptote, or just merging. Either way, it's fine. But the real deal is this one. The probability is the area. So we're going to do a lot of area problems from now on. Therefore, you must brush up your geometrical intuition. We're going to do some geometry problems. Now, let's go over to probability distribution. I talked about the replacements. Yes, indeed. Please recall that for the discrete random variables, the probability distribution was PMF and CDF put together, but we don't have PMF here. Instead, we replace that with PDF, the probability density function. So, the probability distribution of a continuous random variable refers to its PDF and CDF put together. Now, how are they related? Well, not every time we get this nice relation, but this is 1000 level, so at this level, most of the time we get this kind of nice relationship between one and the other. What you're looking at here is a limiting case. The probability histogram that comes from the probability mass function converging into the shaded region underneath the probability density function of a continuous random variable as a limiting case. So histogram versus the region underneath PDF. That's how PMF and PDF is related. And here's another relationship is this time the cumulative distribution function. Remember, CDFs are step functions. We have step, 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 horizontal, and then the jump side is a probability mass. But if we have really a lot of steps, then the jump size gets so small and eventually merge into zero. So we end up with, as a limiting case, a continuous function increasing from 0 to 1. And that's the relationship between CDF. The CDF from discrete case merging into or converging into the CDF for continuous case. We don't always have this kind of relationship, but we do have it in 1000 level, or as a matter of fact, even in 3000 level, we have this kind of thing. Okay, so much for section 1 and continuous probability distribution. Sorry, I went through a bit of a theoretical detail here, and I thought to a certain degree it was necessary. But then again, this was an optional video, so not everybody must have went through this. So I don't feel too bad about talking too much about it.